So I am Damien. I'm developer advocate for video games here at Google. And before that, I have been doing games development for about 8 years. And we all try to build games that are unique. We all try to build games that are special. And yet, they all have one common point. They all have bugs. So I'm going to talk a little bit about how to handle them, especially on Android. Android is well known for being a platform where apps are made in Java. Making games is mostly a C++ job, although some game engines use scripting languages like C#. In both cases, either you are working with C++ directly or with a scripting language, debugging bugs on Android can be a challenge. So let's see how we can make that a little bit easier. There is 3 parts in fixing bugs. The first one is obviously collecting them. If you don't know about a bug and if they are not properly clustered, you can't really fix them. After you have your collection of bugs, you need to find out which one you should be fixing next. It's rare that someone has the time to fix every single bug out there. And finally, you need to get done with it and fix them. So let's see a little bit how the collection part works. While you are developing your game, there is multiple stages in it, obviously. During development, you will likely be using a debug build, and hopefully, you are used to ADB logcat, so you can collect the bugs through that. Then later, during QA, mostly you will be using a release build, and also you will have access to ADB or logcat. And finally, during production, it's a slightly different story, right? Because your user out there will not connect a USB cable, install Android SDK, launch ADB, and send you a crash stack trace by email. So you are going to have to rely on Android Vitals or Crashlytics to get the stack trace back to you. OK, let's start with development. There is a little bit of text on the slide. Sometimes it's a little bit small. Don't read it too much. So that's what you get out of logcat right away when you debug, when you have a crash in a debuggable build, a build that contains debug symbol, I mean. Pretty much right away, it gives you all the information you need, right? I think if you have read that multiple times in the past, you can see that it's a signal 11. You can see that there is somewhere someone that is freeing a pointer that has already been freed before, or not allocated, who knows. And if you look at the bottom part, you can see that there is a function called main_activity _ button2 that is calling another function called HDR record value, in turn calling HDR record values, and somewhere it's crashing in count index 4. Well, that's quite nice to understand which function it's crashing right away without having to do much more work than looking at your logcat. During QA, that stack trace turned out into that. That's a little bit less digest. You get function address, and I'm not so good with understanding that 841E should be some name for a C++ function. So we will see a little bit, we'll see just after that how you can take that stack trace and symbolicate it so that you have the real name and even the line of code that is crashing. And if you look at production, well, in production, when you launch, there is actually no ADB in production. So in production, you will have to use either Crashlytics or Android Vitals. So I think you already heard about both of them earlier today. I'm just going to quickly brush through the difference between each of these. So Android Vitals is pretty much out of the box. If you publish a game on Play Store, and you go in the Play Developer Console, and you look at the Android Vitals section, you will see right away your crashes. And the crashes there will already contain the stack trace. However, the stack trace is not symbolicated, so you will just have, as we had during QA with a release build, you will just have the C++ function address. If you look at Crashlytics on the other side, Crashlytics require an SDK integration. So if you haven't integrated it, obviously it's not working. It's cross-platform, iOS, Android, and support Java, C++, and Unity. And it will symbolicate the stack trace right away in Crashlytics console. So if you go there and you look at your stack traces, you will already have the name of the function of the stack, as well as the line where it's crashing. There is one little detail in Android Vitals that makes it slightly unique. It's that it uploads the crash independently from your game execution. It's really important for one reason. The worst crash you can have in a game is when you launch it, and it's crashing right away. And you try to launch it again, and it's crashing again. If you are in a boot loop, in a crash that happened during the boot, it's very difficult to detect if you are relying on an SDK being integrated, because the SDK will upload the crash while the game is running. But if it's crashing at start, there is no way for the SDK to upload the crash. Android Vitals, however, what happened is that your game crashed during the boot. The crash is being, the stack trace is being registered by the OS, by Android itself, and Play Store will upload it later. So even if you have a crash that happened during boot, Android Vitals will surface it. It makes it very unique. OK, so now let's see how it looks like for Android Vitals. As I was saying earlier, it doesn't symbolicate the stack trace, which means that you will have to do some manual work. The first thing is, go in Android Vitals, copy the stack trace. The second thing is, when you compile your game, you need to keep the debug symbol and store it somewhere in your favorite file system. And after that, you will use an executable called ndk stack that is part of the Android NDK. And with the stack trace plus the debug symbol, you will be able to symbolicate the stack trace. And once you did that once, you just repeat with the next bug. Let's see how it looks like. You go in Android Vitals. You can see that in this sample game I made, there is 2 crashes, one that says new in version 4. If you click on that one, you can see the highlighted blue part at the bottom. That is the stack trace. As you can see there, the stack trace doesn't contain any name for any function. So you copy-paste that stack trace wherever you want in a text file in your development machine. And then you use ndk stack that is part of the Android NDK with your debug symbol on one side, and the last part of the argument will be the text file containing the stack trace. And what you get out of it is a lot of text. Let's zoom a little bit. So that's what I had in my text file originally. You can see pretty much no information for a human. And what you get after executing ndk stack is quite a lot better. You can see that it's crashing in game.cpp line 26 when it's executing a function called button2. That is itself calling a function in game.cpp line 31, calling track stats, and etc. You can see that at the end, it's crashing in a function called hdr_record_value, line 404. Hopefully, you can find 404. OK. Let's see now how it looks like in Crashlytics. In Crashlytics, it's a lot easier. As I was saying earlier, in Crashlytics console, you will already have the stack trace being symbolicated. So right away, you can see that for this crash, that is a little bit different from the previous one, it's crashing line 104 of hdr_histogram.c. That helps you pinpoint exactly where the crash happened. Now that you know exactly where the crash happened, how do you prioritize them? 90% of the time, when I look at a game that people haven't been too careful about crashes in the past, what I see is this kind of separation. I see on the right side, the blue part, very few bugs that impact a lot of users. Obviously, these ones are very important to fix right now. And the green one are somewhat medium amount of crashes that impact quite some users, but not nearly as many as the blue one. And obviously, you will have a lot of bugs that impact very few users. So it's very easy to prioritize the blue one if there is 5 of them. But what happens if there is 100 of them? Or what happens if you have very few blue ones that you can fix very quickly, but you have 500 green ones? So let's see how you can prioritize them. I think the secret there lie into planning for the future. And you need to ask yourself 3 questions to plan for the future of your game in the coming months or years. The first one is, to understand the future, it's nice to understand where you are now. So understand how many impacted users exist right now for one specific cluster of crash. Once you know how many users are impacted, you need to think, are these users growing in size or decreasing in size? A good example is maybe all these users are using an old version of Android that is decreasing in popularity. So maybe this crash will resolve by itself if you wait a week. Or maybe they are all happening on Android 8.0, and it's growing over months. So it's going to be worse in a month. And finally, it's really important to try and understand, based on where the crash is happening, when does it happen in the user session. If it happened very early on, it's probably really bad. If it happened after 15 minutes of gameplay, maybe the user will just relaunch the game. So let's see a bit how you can understand better if it's going to grow or decrease for one specific bug if it's going to occur more or less in a month. If you go in Android Vitals, you have this information for your game right away. That gives you, for each version of Android, how many weekly active users you have. Sorry, in this case, it's monthly active users. And it gives you how it compared to the previous months. So there you can see that 8.0 had 7.5 thousand users, and it increased by 4.7% compared to previous months. And you can see that for each version of Android. I find that a little bit hard to read, so usually extract it in that format. For each version of Android, I have the amount of users, and if it's increasing or decreasing in amount, month over month. So I highlight in red the version of Android I care the most about, and I highlight in green the one that I care a bit less about. And then I take each crash, that's one crash, and I look at which, from Android Vitals, and I look at which Android versions are impacted. In this one, I just put some circle on it that reflects the color on the left, and you can see that Android 8.0 is there, 7.0 is there. That crash is probably somewhat important. However, there are crashes, and I'm pretty sure you have some in your game, that are much worse. That's a crash that was in one of my games. It impacts only all the crashes, all the occurrence of this crash happened on Android 8.0 user. And if you see, over the last months, Android 8.0, I had 7.5 thousand users. This crash happened 7.4 thousand times over the last month. I am not sure if it's a one-to-one relationship between user and crashes, but it's pretty close. So I would say nearly all my Android 8.0 users are impacted. And this crash, month over month, is going to grow by 5%, more or less. So it's really important for me to focus my time on fixing that crash, although the number of occurrences of this crash might be a bit lower than others. If you look at some other crashes, sometimes it's a lot easier. This one, well, there is only one Android 7.0 crash that really matters there. So maybe it's not super high priority, because month over month, this crash will decrease in occurrences by 5%. OK, so now that we see how you collect crashes, and you have a bit of an idea how you prioritize them, well, for fixing them, there is really no trick there. Sadly, that's your job. I can't really help. It's really game-specific there. So let's recap a little bit for today. There is 3 things I really want you to remember from this talk. First one is, please keep the debug symbol. How many times I have seen a developer that launched an APK, have critical crashes, and didn't keep the debug symbol, and is left over with stack traces that contain function address and no way how to read them. It's quite sad. So even if it's just by pure safety, because your game has 0 crash right now, every time you compile an APK, keep the debug symbol. If you don't know how to get the debug symbol, you can search for it. It's really not that difficult. Second thing is, Android Vitals, even if you don't care about your crashes too much, go take a look at Android Vitals. It will help you understand how bad the problem is. Truth is that, hopefully, the problem is not so bad for you, and you don't need to focus too much time on it. But maybe you will find out that your users are having 5% crashes every day. And in that case, Android Vitals will be able to help you understand if you need the help of Crashlytics to debug all these crashes. As I showed earlier, Android Vitals plus NDK stack can be a little bit cumbersome to work with the stack traces, but it works. If you see that you have 50 crashes, that's fine. If you have 500, maybe you want to think integrating Crashlytics so that it simplifies the stack trace right away. And finally, well, now that you know that there is a way to fix your crashes in your game, well, you should really come to the next session, where Bill will talk about how you optimize the performance of your game. Thank you very much.
OK. Thanks, Damien. So let's talk a little bit about why you might want to optimize your game. One of the obvious reasons is to get better-looking games. Who here doesn't want their game to look better? Now, with all that extra rendering you'll need to do, you'll have to optimize the game to still make it run fast. Another reason is to make the game more responsive. And this is important for games that are very competitive, like multiplayer games, or games that require quick response time because they're fast-paced games. You should also optimize for memory because you don't want your game crashing because it runs out of memory. And you should consider optimizing for power because these are mobile devices. They have a battery, and you want the players to be able to play the game a long time without running down the battery. The other reason is because power is related to heat. And when the device heats up, the system will throttle the CPU, which will cause it to run slower. So let's look at some CPU performance optimizations. One of the best things you can do is to do multi-threading. So high-end Android devices have 8 cores, and it's really a waste to just not use some of those cores. Single-threaded core, single-threaded game is a waste. So one of the things we know is that that multi-threading, and of course concurrent multi-threading, which is really the optimal way of doing multi-threading, has better performance per watt than single-threading. So it affects power as well. You've probably all heard that it's good to batch, and this is still true. Every draw call has overhead with it, driver overhead with it. So if you can combine draw calls into a single draw call, that's going to help with that CPU overhead. Game engines like Unity, they have options for doing dynamic and static batching, which can help with that. The other thing you want to do is not draw things that you're not going to see. So things like frustum culling and occlusion culling are important. Vulkan is a good API for reducing the draw call overhead. The Vulkan API doesn't require validation being done for every draw call, and that's how it saves time. The other thing that's good about Vulkan is you can build command buffers using multiple threads. And so now this takes advantage of multi-threading, as I mentioned earlier. You don't want to overlook loading times. The reason is because loading times can affect if your players are going to continue to play the game. If it takes too long to load the game, it may not be worth it to them. So some of the things you can do to improve loading time include just pick a good compression format. So one that decompresses fast. An example could be LZ4. The other thing you want to do is only load what you need. You don't want to load the entire level when you're only going to be, you don't want to load the entire game when you're only playing one level. The other thing you should do is to hide the loading. So even though you're still loading the game, you don't want to make it obvious like having a big loading bar, like in this diagram. So something you could do is like when the user is navigating through the menus, you could load things in the background. And for Unity, IL2CPP has been shown to have really good performance. So even for not just loading, general CPU performance, you should use IL2CPP. So we're going to be asking developers to use 64-bit and have a 64-bit version of their APK later this year. And this is also a good thing because 64-bit gives you better performance. It can because the 64-bit instruction set has access to twice as many registers as a 32-bit instruction set, even though they're running on the same device. Because of this, the compiler can use those registers to do better optimizations and make your code run faster. So now let's take a look at the GPU side of things. One of the most common reasons for a game to be GPU bound and to spend a lot of time on the GPU is when it spends time in the fragment shaders. So the more pixels you're rendering, the more time it's going to take. Now, modern devices, they have incredibly dense displays, and so it's really overkill for most games. you can render a game at a much lower resolution, and it'll still look just fine. Now, you might be thinking that, well, when I render it at a lower resolution, the problem is the text starts to look blurry. Well, a couple of things you can do. One is you can reduce the resolution in one dimension, just either vertically or horizontally. That can help. Another thing you can do is you can render the text or the HUD at full screen resolution and composite it with the lower resolution version. Now, you can do this in a fragment shader. For example, if you're doing post-processing anyway, what you can do is combine that with the upscaling and the compositing. And then in one step, you can get that combined. The other thing you can do in some cases is to use the hardware composer. All Android devices have hardware composers that can composite multiple layers of images. So if it's not fill rate bound and pixel shader bound, it's the other end, which is geometry bound. So you want to reduce the number of vertices. And the way to do this, the common way to do this is, of course, to use LODs. Now, some GPUs are more capable than others. So what you can do is adjust that LOD distance based on the capability of the GPU. So higher end GPUs, you can extend that high detailed LOD out further. The other thing you can do is take that to the extreme and have imposters, which are just 2D geometry with textures to represent 3D geometry. And when something is far out on the distance, it looks fine. So now getting back to responsiveness. The important thing about responsiveness is consistent responsiveness. One of the things that happens is if that responsiveness is not consistent, if that touch latency isn't consistent, the game just kind of feels wrong. Like it has a bad feel to it. Here's an example of a game that was captured with systrace. And you can see the actual frame times for individual frames. Some of the frames are fast, some are slow. But interestingly, it all averages out to 30 frames per second. So if the only thing that you're measuring is average frames per second, this will be completely overlooked. With Android, one of the things you can do is use the choreographer API. And this allows you to register callbacks that happen every VSync, which you can use to synchronize your rendering. Now, you want to optimize for power, as I said, because it's important on mobile devices. Some games really do work better with 60 frames per second. But most games, slower paced games that aren't fighting games or something like that, they can run well at 30 frames per second. So even if your game can run at 60 frames per second, it's better for it to run at 30 because you're saving so much power. You're doing half as much work. Also, you want to consider offloading things to the GPU. The reason is the GPU is more power efficient. It does things in more things in parallel than the CPU. An example could be doing animation on the GPU, like GPU skinning. Thread affinity is a great way to manage power. Linux gives you the ability to manage threads with thread affinity. And as you can see in this example, you don't want to schedule all of your threads necessarily on the big cores. The big cores are typically cores 4 through 7. The little cores are the first cores 0 through 3. The little cores aren't as fast, but they are more power efficient. So if you had a thread, say, for example, that wasn't really performance critical, say it was doing something like asynchronous loading for streaming assets for future frames, then you could probably put something like that on the little core. So now let's look at memory. Optimizing for memory can be difficult on mobile devices. One of the reasons is you're not always sure how much memory you have available to you because you're sharing the memory with the system, with other apps. And so you can't expect to use all of that physical memory. So let's take a look at this, for example. This is a Pixel 3, and it has 1.5 gigabytes for system memory that's used by the system. Now, you can't expect to evict all that memory and use it all for your game. So on a 4 gigabyte system, in this case, you might be able to use like 2 gigabytes of memory. Now, if you want to reduce the amount of memory that your game is using, one of the things you can do is use a shader cache. The shader cache, an LRU shader cache, is actually used by the Unreal Engine, so you could use that feature. So the way it works is you can make sure that only the shaders that you're interested in, that you're using, are cached in the GPU memory. OpenGL and with Vulkan both, you can extract shaders from the GPU memory, compress the binaries, and store them in CPU memory. Now you're trading off GPU memory for CPU memory, but that's okay because it's all the same physical memory because it's unified memory architecture. And finally, for testing memory, one thing you want to consider is testing on real-world situations. For example, you want to test on devices which have a lot of apps installed. We found that when you have some apps installed, they can take up memory, even though you may not expect that. So you don't want to test on a clean device.
So I'm here for the comic relief part of our day. And this talk is about rogue permissions, and I'm sure you're wondering exactly what that really means. And so I have a visual aid. Essentially what we're talking about here is what happens when you're writing a game. Much of the code that is actually going into your game is stuff that you actually haven't written. And so rogue permissions in this case are permissions that are not used by the game itself, but are instead used by the libraries and tools that your game depends on. So for this talk, rogue really refers to code that you didn't write. And I probably should have entitled it something like, be wary of rogue code, but I digress. And you're also probably wondering, am I going to keep this accent for the rest of the talk? And the answer is, I will not. So what I wanted to point out here is that we are, when we're talking about these things, we are talking about this combination of privacy and performance equals policy, or to alliterate, we passionately pledge to promote privacy and performance, which leads to pertinent policy. And an example of this is, when you're looking at a library or SDK, you really need to be asking yourself a bunch of questions. One is, does this library or SDK actually want unnecessary access to sensitive data? And the second thing is, what impact does it have on the app performance, or even worse, on system health in general? And so let's say something that a possibly rogue code might need is the location permission. And now, first of all, there's two types of location that it might need. There's coarse location and fine location. And honestly, to your game, it really doesn't matter because on Android M, they're both kind of bad because you end up having to pop up this runtime permission, and it's really terrible. And most likely, your app libraries aren't going to be needing this because of that. But if they do, it's really important because users need to be informed that not only is this app able to track sensitive information such as their location, but also that the device is likely to drain their battery much faster. And and in Android O, we actually attempted to mitigate some of the battery drain problems with location by limiting how often background apps actually get access to this location data. And we honestly still have more work to do here. So the moral of this story, so to speak, is that location, as an example, is an intersection of performance and privacy. And this influences both the way that the Play Store as well as the platform look at policy. So again, there's a whole bunch of these permissions, and if you need to have access to any of these kind of sensitive permissions, you really need to understand why this is happening. It's very, very important. Now, one of the things you should look for is that Android library projects, these SDKs and tools, can include library permissions. So they actually have their own Android manifests. And once again, we can use our favorite tool, the APK Analyzer, to actually look at all of the permissions that your app is actually going to end up requesting. And it's really important, again, for you to understand why your game ends up requesting each one of these permissions. Now, plugins also are libraries, and so they can also contain permissions in native code. So we want to make sure they're also compliant. And finally, we want to make sure that you are testing with the latest target SDK. These things are important. If you saw in Damian's talk earlier, you can actually end up with crashes that only impact certain SDKs. So you want to make sure everything works as expected, so you can use things like play test tracks, which are very, very useful. And now for something that can also be a real problem for code that you don't write, and that is 64-bit. And now I know what you're saying. You're thinking, okay, this has nothing to do with permissions. I'm totally going off the reservation here. But it really is something you have to think about when choosing your library or SDK. And besides, we know from the history of video game console marketing that 64-bit is just cool. So moving to 64-bit will actually make your APK size larger. But it will also typically make your game run faster, and there's lots of reasons for that. The 64-bit instruction set was actually designed for performance over things like code size and other things, and it actually has double the registers, but more importantly, it actually does things like supports double precision floating point in neon code. So your compiler can actually do really clever vectorization and really, really improve the performance of a lot of heavy floating point stuff. And it just turns out that games actually take a lot of advantage of floating point. So the good news is that this won't actually make your APK size that much larger, having a 64-bit binary, if you move to Android app bundles. We've talked about these a whole bunch. These are great because it actually strips out the unnecessary binaries when you distribute your game with an app bundle and using Google Play App Signing. So if you have a 32-bit and a 64-bit binary in your app, the device will only get the one that it actually needs the most. And while you're at it, you can do things like bundling x86 and x86 64 support with no size penalty to your ARM apps. And these versions will actually work better on a lot of Chrome OS devices. So with performance implications, this has, of course, become a Google Play policy decision, at least initially. So by this August, all new and updated games must include a 64-bit version. Now, there is an exception for Unity when targeting Unity 5.6 or less. Google Play will continue to allow updating games built with these older Unity versions for another 2 years. And then it won't deliver any 32-bit games to any 64-bit capable devices. Please do not go out and port your games back to Unity 5.6. There's a lot of really good reasons to actually run the newer versions of Unity. Now, of course, Google also hasn't made any guarantee that we're actually going to have non-64-bit only devices by this point either. Note that you need 27.4.16 or if you want to run 64-bit code, or 2018.2 or higher, because 64-bit was actually ported back to 2017.4.16. Another thing you'll need to do is switch to the IL2 CPP backend, and that'll mostly make your game run faster, so it's actually a win-win. So some tips for going 64-bit. One is, once again, you can use our favorite tool, the APK Analyzer, to see what 32-bit dependencies you might have. And you can examine all the files in the lib folder. The 32-bit libraries are in the ARM EABI v7a, or even v5, if you still have them, and x86 directories. Next, you can do a 64-bit build. So, Cocos and Unreal and Unity all support 64-bit code on Android with the correct settings. And also, Gradle, CMake, and NDK build can easily add 64-bit targets. Now, obviously, there's a lot of work that you do have to do to make sure that everything in your native code is going to work correctly with 64-bit. I'm under the assumption that since many of you do publish on other 64-bit platforms, that most of this code and this work has already been done. But there is definitely some work to make sure that you are doing all the right things in 64-bit. You also may need to upgrade SDKs and libraries to more recent versions. And this is an opportunity to reach out to library owners if there are 64-bit ready versions that aren't available. And this is also a really good time to examine the real need for all of these external dependencies. It's amazing to see when you actually go through and audit all of the things that are in a game, all of a sudden it's like, oh, my APK size is now 20% smaller because it turns out we didn't really need this anymore. So it's really good to go back and do this on kind of a regular basis and take a look at all the stuff you're putting into your APKs. And finally, there is testing. You'll want to test locally. This is another great example of using Google Play's test tracks. You'd also take advantage of things once you're doing this, like Android Vitals and Crashlytics. All these things can help you get a really good idea of how your game is actually performing in the real world. Now, once you've actually tested this, you can leverage stage rollouts to make sure that your users have the smoothest experience. So again, there's a lot of things you can do to test this to make this experience great. Again, mostly 64-bit should be a win-win for both you and your users. So 4 straightforward steps to get your game to 64-bit. Now, there is a moral to this story, and that is performance matters to us and hopefully to you. And it's something you should consider when choosing any code that you didn't write to ship with your game. So when you're examining whether or not to use a new library or SDK, make sure that it works with a true 64-bit app. Another thing to think about is API-level targeting. Now, for an app or game to be permitted to update on Google Play, it needs to target the latest Android release within a year of its release. Now, currently, that means targeting 2017's Oreo, but not for much longer, because as of August, it will actually mean targeting 2018's Pi. And you need to make sure that any library or SDK that your game depends upon actually supports targeting the latest API release. And this is important because there actually are some Android behavior changes that are tied to the target SDK version. Now, Android, in many cases, actually preserves some out-of-date functionality for apps that are targeting older SDK versions for the purposes of compatibility. Now, libraries and SDKs can also do things like impacting launch speed. Now, you can often mitigate this, of course, by deferring loading of these libraries, but some libraries will do things like requiring initialization in the application class, which gets initialized before most of your code, or less obviously, they'll even contain a content provider that makes sure that the app is initialized before even, that the libraries, is even initialized even before the application code runs. And this is really only a reasonable solution if you're doing things like crash analytics, because obviously you want your crash provider to be initialized very, very early. And there we are. Fortunately, you can use the systrace tool to profile your launch speed and see the impacts of libraries and SDKs. Now, sometimes you might have so much data coming in here that actually systrace isn't a great tool for that, so you can also leverage SimplePerf. Launching faster, as we've said before, means your game will likely be played more. And with any luck, that'll translate into dollars. And we've got some great videos on YouTube that show how to use systrace to optimize launch speed and profile other performance problems. Now, Google Play has its own policies, and you need to make sure that the library doesn't violate those. And this is because Google Play really does have a critical role in protecting the privacy and safety of Android devices. As an example, apps aren't allowed to sideload code changes. Google Play has actually had to unpublish apps when SDK providers have done things that violate Play policies. And of course, multiple violations get an account banned from Play, so this is really important stuff. And then there are things that I have absolutely no ability whatsoever to advise you on, other than I strongly to encourage you to make sure that code that you don't write is compliant with all necessary policies and regulations from various entities around the world. And of course, you should test the library against the latest Android version you can, such as our recently released Q beta. These are all of the desserts I could find that begin with Q. Q actually makes changes that continue to improve Android's speed, privacy, and safety. Now, it continues our work on location by actually giving the user an option to allow a game or app to only access location when in the foreground. It also limits access to device and hardware identifiers, such as IMEI or serial number, IMSI, and it actually automatically randomizes the MAC address across different Wi-Fi networks. And this is important because a lot of ads and analytics packages may not function correctly if they weren't already using the appropriate identifiers. And of course, Q is bringing a whole bunch of updates around performance, including, very exciting to me, support for Vulkan 1.1. We also are doing something kind of cool. I don't know if you've noticed this in our announcement. We're actually supporting, experimentally, OpenGLES 2.0 running on top of Vulkan through the Angle project. And this is great. It's not really going to affect performance, but we hope it will actually lead in the long term to more stable OpenGL drivers and more stable Vulkan drivers. And we're also doing this really cool thing in Q we're called cloud-based profile-guided optimizations for art. So this means that code that's actually running inside of managed code on your app will actually get profiled and optimized more quickly, which of course just means that your users are going to see better performance more quickly. And of course, the best thing you can do is to test your game against the current beta. Try running your current build and consider testing running a build that actually targets the Android Q SDK. And you can find out all about this at google.com/android/beta. And right now, we're currently supporting Pixel and Pixel 2 and Pixel 3 and the various XL versions of all of them. So at least this is a good start with devices, and you can sign up right there, and we will deliver the beta to your device wirelessly. And that's it. So here's a bunch of resources to find out about getting your apps ready for 64-bit, as well as some best practices around that, and of course the beta. Up next is our final talk from Ben about how you can extend your games beyond mobile.
As Dan mentioned, I'm Ben Gable. I'm a partner developer advocate at Google, working with game developers. And today, we're going to be talking about extending Android games beyond mobile. And what do I mean by that? So, whoops, that's the laser button. So mobile gaming is evolving. And just a few years ago, mobile gaming used to kind of mean games you play on your phone. But now it's not so clear anymore. The Android ecosystem is evolving, and Android now runs not only on phones, but on tablets, desktop extension devices like Chrome OS and Samsung DeX, and coming very soon, the exciting world of foldables like the Samsung Galaxy Fold. So maybe just a quick question for the crowd. How many of you have purposefully optimized your game for a device that's not just a mobile device? Show of hands. Anybody? I see like 2 hands. Okay, how many of you are actually planning on maybe this year with your next game, adapting your Android game for a device that's not just mobile? Anybody? Okay, a few more hands. So hopefully at the end of this talk, there's a lot more hands that go up. But the key point that I want to drive home here is that as game developers, you need to consider that your game is not just going to be being played on mobile devices anymore. Players might be playing it on a phone in a portrait mode. They might be playing on a Chromebook or DeX with a keyboard and mouse attached to it. They could be playing on a foldable with multiple displays, so when they switch open from the small screen to the large screen, the resolution and aspect ratio changes. This is really important to kind of start thinking about this because as game developers, you guys want to provide the best possible gaming experience for your players, no matter what device they happen to be experiencing your game on. Now, I realize that the words new platform or like supporting an additional platform is kind of scary for a lot of developers. But what I really want to stress here is that this is all still Android. And by following the Android best practices, you're going to get a great baseline experience and compatibility across all these different devices. So certainly there's things you can add specific to foldables or tablets or Chrome OS. But I really want to focus on the core things, the stuff in the middle there. That's going to give you a great experience with kind of the least amount of work. And hopefully I boiled it down to 3 main areas you need to consider. And that is screen considerations, input considerations, and how to build and kind of set up your APK so that when it's distributed, it can support the most devices possible. So let's start off with talking about some screen considerations. What do I mean by that? So when your game is launched on some of these other devices, like a Chromebook or Samsung DeX, by default, your game is going to be launched in a windowed environment where it can be dynamically resized. And on foldables, it'll be launched in an environment where if the user opens the device up from the smaller screen to the larger internal screen, the aspect ratio and resolution is going to change. So the most important thing here to support is what we call configuration changes. And for those of you that are not familiar with the idea of configuration changes, basically the Android system will restart an activity every time it detects that something has changed about the environment that your game is running in. By default, the system does this automatically by invoking onSaveInstantState before your activity is restarted. However, for a lot of resource-heavy games, this is not the best approach. It can be really slow, and especially in the cases of things like dynamic resizing, where you could be getting configuration change events every frame. It just doesn't work. So what we recommend as a best practice is to handle these configuration changes yourself. And you can do so really easily by inside your manifest declaring all of the configuration changes that you want to handle in code. So in this example, we've said we want to handle screen size and orientation changes ourselves. So then once you declare all the configuration changes that you want to support, inside onConfigurationChanged in your activity, you can, whenever that change happens, you now get an event, and you can handle whatever that change was. So for example, you could scale your OpenGL content to match the new resolution or the aspect ratio to prevent things like inaccessible UI elements or input areas that don't make sense anymore with the new resolution of your game. And if your game is always intended to be run in full screen, for example, or maybe you've got some bugs and you need to quickly iron them out, you can always prevent resizing by specifying resizable activity equals false in your manifest. But keep in mind that this will prevent split screen operations of your game. And we don't really recommend it because it is a valid user experience to have like your game running with Twitch chat or something else in those kinds of windowed environments. So we recommend supporting it whenever you can. For orientation, for mobile devices, orientation is by default portrait. But on other devices, it could be landscape. So it's important to make sure that in your manifest, the best way to kind of handle and tell the system what kind of orientations you support is to specify your sensor orientations in your manifest. Now, if you're handling orientation changes yourself in code, you want to make sure that you're using display.getRotation, as that will give you the accurate information you need in order to determine which orientation the device is in. But be aware that the values you're expecting with display.getRotation might be swapped depending on what the hardware's default orientation is. So just be aware of that. Also consider the resolution of the device that you're playing on. So a bigger screen means you should provide higher resolution assets. You can use app bundles, as has been mentioned many times today, to kind of package all your assets and have Google Play deliver only the assets that are relevant to the device that your player is playing on. So for example, omitting ultra-high resolution assets if they're playing on a mobile device, or only serving up the ultra-high resolution assets if they're playing on something like a Chromebook or a high-resolution tablet. This saves you valuable download space, which is always a win, and also the trouble of maintaining multiple APKs for all these different screen densities. And with more pixels comes greater flexibility on UI and HUD design. So if your players are playing on a larger screen, consider what kinds of elements you can expand, add, change to take advantage of that particular display. Also, players tend to sit farther away from a screen the bigger it is, so make sure that all of your fonts and elements are identifiable and readable. Nothing more frustrating than having to squint at a large screen. So that's some screen considerations. Let's talk about input now. So more and more games are delivering a console or PC-like experience on mobile, and more Android devices are now offering multiple ways of input. So although Android has had APIs around for a while for things like keyboard, mouse support, and controllers, most game developers just assume that they're going to be playing with touch controls. And that gets really frustrating when players download a game that's maybe been ported from a PC or console, and they try to use keyboard or mouse on a Chromebook or something like that, and it doesn't work. It's a pretty frustrating experience. So the other thing to keep in mind is that also many of these devices are convertibles. So they can change between different configurations on the fly, such as clamshell with keyboard to tablet mode. So it's important to kind of detect those changes and support on-the-fly control schemes that provide the best user experience at the time, and try to anticipate what you think the users might be expecting the control scheme to be at that particular time. So the best way to do this, as I mentioned, is to detect the hardware that's available and support a control scheme that will give players the best experience. So to start, you might declare, again, support in your manifest to handle configuration changes related to inputs like keyboards being attached and detached. And there's many ways of doing this, but essentially you could then query Input Manager whenever that input change is detected or at game startup, and figure out what kinds of hardware are available for the players to use, and then switch the control scheme on the fly based on that. Now, another key point to remember here is that just because Input Manager says that something is available, it might not be usable. So it could be like a Chromebook with a keyboard that's actually in tablet mode, so the keyboard's on the back, and it's not usable. So again, just kind of keep in mind that these devices are convertibles, and that your players may switch between any number of control inputs at any time. And if you don't think keyboard support makes sense for your game, fair enough. But you might consider that implementing it will improve the accessibility of your game for lots of people. So some ideas could be skill key bindings, menu, player navigation. If you really want to get fancy, you could implement custom key mapping so players can set up whatever they want for specific keys to do certain actions. So it's all up to you. We highly recommend that you do think of this for players that are playing on these devices with keyboards. And also, if you haven't implemented controller support yet, consider that the standard Android controller APIs work on devices like Chromebooks and Samsung DeX, where controllers might be more widely used. So we've talked about screen and input considerations. So finally, let's talk about some general considerations around building and kind of configuring your APK to make sure it supports all these various devices running Android. So first off, review the permissions that you're asking for and determine if you really need them, as kind of Dan alluded to in the previous talk. Some permissions are not supported on certain devices, like Chrome OS. So blindly asking for permissions or features that aren't supported will put you in a scenario where the user will try to download it from Google Play on that device, and it will show up as not compatible, and they'll have no idea why. So it's kind of a bummer. Good examples of this might be GPS or SMS permissions. And what we recommend is basically you can list these features or permissions as not required in the manifest, and then just check in code to see if that's actually available. So that way users can download it, and then you, on your end, inside your code, dynamically kind of adapt the game to either use those features or not, depending on what device the players are playing on. Also, consider the hardware and performance capabilities of the different devices you're running on. So if you have an automatic quality control system, or you have different kind of performance profiles, try to set them up in such a way, well, first of all, test them on these different devices like Chromebooks and tablets and foldables, but then consider setting up different profiles to take advantage of all the extra hardware and performance capabilities of those devices. You want to make sure that players, when they buy a bigger device, they're expecting more performance out of it. So make sure that you're kind of thinking about that. Additionally, try to provide an x86 build. So many Chromebooks are x86 only, and while ARM will still run on them, you're going to be incurring the instruction translation overhead, and will degrade performance a bit. And for those of you looking to get the maximum graphics performance, again, we suggest you use Vulkan, as they're now supported across many devices, at least 1.0, with 1.1 support coming very soon. And finally, test across all these different devices is probably the biggest suggestion we can make. So add test cases that cover all the additional flows like resizing, minimizing, maximizing, switching between the small and large screens, You want to make sure that you kind of see how your game is behaving in all these scenarios, because you might only be testing on a mobile device, and bad things could be happening. You can use things like the Android or Chrome OS emulators to kind of get a sense of how your game might behave if you don't have those devices available. Or you could use Firebase Test Lab to help you automate the process, since probably not a lot of you are too thrilled about having to expand your QA teams to kind of test all these different devices. So there are a few tools out there that you can use to kind of help yourself in that area. So in closing, the thing that I really want to stress here is that Android gaming is not just phones anymore. Players are experiencing your game on a wide variety of devices and form factors with different inputs. And by following kind of these Android best practices and spending just a little bit of time considering the additional use cases that players might be coming across, you can really take your game beyond mobile and provide the best possible gaming experience for your players. And they will thank you for it.